Three blocks with masses m, 2m, and 3m are connected by strings as shown in the figure. 3m, 2m, 3m. Upward force F, constant speed V. What is the net force? See, the direct answer is the moment you see it has constant speed, what is acceleration? Acceleration is d by dt of velocity or speed. So what is constant here? Velocity is constant, so it is d by dt of a constant, which is equal to 0. Therefore, the correct option is 0. But that's not what we want, right? We want to learn the concept behind this. So let us first try to understand the way to draw excuse me, way to draw the direction of tension. Okay. Again, one common doubt which students often ask me: how to find the direction of tension. I'll explain you a couple of examples, then things will become absolutely clear to you. So say this is a fixed table. Okay. A body of mass m is kept here. Okay. There's a string here, sorry, a point of contact here. Point of contact. It has been, two strings have been connected. Okay. And it is pulled by one force F1 on right side and another force F2 on the left side. Let me make use of a larger diagram. And suppose that you have a suppose that these are fingers wrapping this rope here. Okay, why fingers? Because we need point of contact. So what is the direction of tension? It's pretty straightforward. Direction of tension is always acting such that it is away from the point of contact. Acting away from the point of contact. Let us see. So this rope here, if it has tension T, okay, if it has tension T, it has 2 points of contact, one from the block and the other at the finger, right? So point away from the point of contact, acting away from the point of contact, say tension T1. Okay, let's do one more case. There are 2 points of contacts here. So where will tension act? Acting away from the point of contact, say T2. Again, we have point of contact here, acting away from the point of contact here, tension T2. Okay, simple example. Let's take one more example on a case like this. So a pulley is attached here. Pulley is attached. We have, wait. So say we have a string like this. We have a string like this. And at the end of the string, there is a mass connected here, say of mass m. Another string like this, say mass m. Okay. Now in this case, let us try to draw the direction of tension. See, now this is only one string, right? There's only one string present here, so the overall direction would be t. So the overall magnitude would be t. Now the direction of this, see, let us first identify the point of contacts. This is sorry. So say this point over here between the string and the block is one point of contact. There is one between the string pulley here, another between the pulley here, and the third one again with the pulley and the block, right? So how do you draw the direction? Away from the point of contact. How do we draw the direction of tension? Away from the point of contact. Tension T. Tension T. Point of contact, away from it. Again, point of contact, away from it. Tension T. Excuse me. So I would say this is the logic behind drawing the direction of tension. Okay. Having said this, let us move on to the question here. So I'll keep this as a reference, right? The direction of motion or direction of tension. And I'll draw the complete diagram. I'll enlarge this. I'll keep it as a reference. Okay. See, there's a minor correction here. Actually, this string is not present here. Yeah, something like this. Okay. Now let us draw the blocks individually. Yes, that is what I'm trying to cover here, is to make sure that you are able to solve any question using this concept. So the force acting here, right? And between M and 2M, there is one connection. Now, since there is only F acting here, there's only force here. But here there's a point of contact between string and the block, which means there would be tension acting downwards. That I'll write as T1. Okay. Now, we have another block here, which is 2M. Now look at that. 2M has two strings connected, one towards M, the other towards 3M, right? So there would be point of contact here, string, point of contact here, string, and tension would be acting away from the point of contact. So we'll have here T1 and it is acting away from it. We'll mark it as T2. Okay. Now let us see with the case for the third block, which is the block with mass 3M. There is nothing acting downwards to it, but what is acting is force like this. There's a string, right? And tension would act along the string but away from the point of contact, and we have here T2 again, right? Same string. Now what we'll do is we'll try to club these diagrams together. Okay. So this is 1, this is 2, right? I hope you are able to decipher the concept here. And this is 3, right? So now that becomes the overall free body diagram. Okay. Now we'll also draw the free body diagram for the complete set, which means it goes like this. Add the overall masses. What are the overall masses? M, 2M, 3M, right? So I'll replace this complete this whole set of blocks with one big block, which measures, it's better to write down, I think, which measures M plus 2M plus 3M. What is acting on it? F is acting on it, which means the net direction is actually towards the positive direction upwards, positive J, positive Y axis. And it is given that the overall system is moving with constant velocity, right? See, from the figure, it can be very safely assumed that this complete set, if there is excuse me, if there is a vector force acting in the upward direction, it means that the blocks are moving upward like this, right? It's moving upward like this. It is not coming downwards. This was the original position. The block is moving upward like this. The block is moving upward like this. So it's here now. The block is not having any kind of horizontal movement. The block is not having any kind of horizontal movement. It is having only vertical movement. I repeat, the block is not having any kind of horizontal movement. It is having only vertical movement, right? So if you have to compare this diagram alone, the object is moving, sorry, the block when combined together, the block is having only vertical movement. It is not having any horizontal movement, which means if motion is along y axis alone, if motion is along y axis alone, it means that force along the x component is equal to 0, right? It means acceleration along the x component is equal to 0, because there is no force, there is no motion, there is no acceleration, there is no velocity, there is no acceleration, there is no force. Simple logic, okay? Which means the complete motion is now restricted to towards the y-axis. Now, the forces acting on this body would be Fy, right? And sum of all the Fy would actually give us the excuse me, would give us the F net, which would result in A net, right? So if you were to write the equation here, how do you write this? We can write that sigma Fy is equal to m into A net, right? Which is equal to m into Ay. Why Ay? Because Ax equal to 0. Now, since the object is moving with constant velocity, acceleration along y direction would be equal to 0. So we have m into Ay is equal to m into 0. Therefore, sigma Fy is equal to m into 0 is equal to 0. Okay, so sigma Fy is equal to 0 is what we derived. So what is the net force in the block of mass? 2m. So if we were to study only this block 2m, if we were to study only this block 2m, what we need to understand is we need to understand the free body diagram of 2m alone. So let us draw that one more time. So we have 2m here. Tension is acting away from the point of contact, which is T1. Tension is acting away from the point of contact, which is T2. So what is sigma Fy? Sigma Fy will be the difference here. The net direction of motion is acting upwards, so we'll take that force moving along this direction as positive and that moving opposing this direction as negative. So we have sigma Fy is equal to T1 minus T2, right? Now, this is sigma Fy is equal to T1 minus T2, and what would be the acceleration? This will be equal to mass into mass, which is 2m into all the bodies will have the same acceleration, right? So it will be 2m into A net. So we have T1 minus T2 is equal to 2m into what is A net? We derived it. A net is equal to 0. Therefore 2m into 0. Therefore, in addition to this question, you can also maybe asked in a different way that T1 minus T2 is equal to 0, and therefore for this condition to exist, T1 should be equal to T2, and the sum of the forces acting on this is actually equal to 0. So I think this explains the overall application of direction of tension and how to resolve the forces along the x and y direction. If you want further explanation on tension, please post it after the class. Those students who are listening this online, you can post a comment. Okay, so Yes, that's it. So maybe if you want, we can discuss multiple cases. One block on another block, maybe two or three blocks being connected by strings on a horizontal plane, on a vertical plane, on an inclined plane. All this we can resolve tension as we did in the second question for mg. Like mg cos theta, mg sin theta. We can have t sin theta, t cos theta. Those kind of questions. If they are in the previous questions, I'm pretty sure they would be. We'll have a detailed discussion. If not, if you want any question in specific, please, I request you to post it. You can write it directly to me, or you can post it in the comment box. We'll get back to you. Okay. uh, yeah, so that being said, let's move on to the next question number 4.